All right, hey everybody. Happy Monday to you all. Great, hope everybody's doing well, staying warm, all that. So the plan for today is to kind of finish what we were discussing last time on worksheet 18, which was dealing with eigenvectors and some loose ends that we need to tie up on that worksheet, and then moving on and starting worksheet 19, which deals with nonlinear systems of differential equations. So that's chapter 8 of the reading materials. So just so you know, this will conclude this stuff that's going to be on your next exam. So this week we're just going to work on worksheets 18 and 19. And then next week we'll start some material, but that stuff won't be on exam 2. So exam 2 will just be on the stuff that we did in chapters 3 and chapters 8 with systems. So any questions before we get started today?
Yeah, I had just a question on homework number 7. Only problems 1 through 3, because I saw it, 4, we're going to conclude that on homework number 8. But there was something on the third problem where it said, like, use the technique from the last week worksheet, or not worksheet, homework. Aren't we doing the exact same thing for number 2 and number 3? I solved it the same way, so I got a general solution, X and Y.
Yep, so 2 and 3 are both asking you to do the same thing, solve the systems as we did in worksheet 17. Yeah. So
okay, cool.
like finding the eigenvalues, plugging them in, finding the other one. Yep.
Okay,
so yeah,
cool.
Sorry if the instructions were odd, but yeah, they're just asking you to do the same thing in question 2 and question 3.
Okay, sounds good. Thank you.
Yep. Anything else? Okay, so
up until homework 8 will be on the exam?
Up to and including homework 8. So the stuff that we'll have due for next Monday will be the stuff we work on this week. So that stuff will be on the exam. Yeah. And then starting next week and after the exam, we'll talk about chapter 6 in the reading materials on Laplace transforms. And that'll be the last bit of material for this semester. Hard to fathom that we're almost done. Maybe it feels like we should have been done. I don't know. It's going fast. Okay, so any other questions? Okay, so let me just start with the example we ended with last time, which was down over here. We talked about what an eigenvector is. Then we talked about how we can find them, and then how we can use them to express solutions. And I just want to kind of go through that process again, since that's where we ended things. So want to make sure that is clear. So first thing is we define this thing called an eigenvector. Right, by saying we have a matrix, and here it's implied that this is a square matrix. We can find eigenvalues for that matrix, and then for each eigenvalue, we have what are called corresponding eigenvectors. And so the equation that an eigenvector needs to solve, it's going to be, we should say, first of all, this is a non-zero vector that satisfies this matrix equation. So in other words, multiplying that vector by the matrix A is equivalent to multiplying that vector by this scalar lambda. So I want to just kind of give you a chance to make sure it's clear how to find these, and then we can talk about how we can use them. Okay, so here's the example we took a look at last time. So let's say we have this system, x prime is 3x plus 10y. Y prime is minus 2y. And we want to find eigenvalues and eigenvectors for the corresponding matrix of coefficients. So here we can find the eigenvalues. We've done this before. These are 3 and minus 2. And so when you're showing your work for these, oh no. think I erased stuff back there. Okay, sorry. I didn't realize my welcome got put on top of my work. I think I can salvage most of this. Okay. So we start with this matrix, and the equation that we have here is we want to find some matrix so that when I multiply by matrix A, which is 3, 10, 0, minus 2, times this matrix B, we get the same thing as if we multiplied by the scalar 3. And so when you're showing your work for these, it's going to be nice for you to like organize your work to say like step 1, here's the matrix. Step 2, we can find the eigenvalues. Step 3, we're going to find the eigenvectors, and just clearly organize your work so that it's clear. Here I'm finding the eigenvectors for which eigenvalue, since there's going to be multiple ones. So we can start with 3 again. So that means this equation over here, we plug in 3 in place of the lambda, and these were the resulting equations that we get. When we multiply that matrix out, and then we want to solve these equations for A and B. And again, what you should find is you're not going to get that A is 5 and B is 6, but you're going to get an infinite number of solutions here. There should be many, many different eigenvectors that we could give. And we only want to find one. And so then we solve this equation. And so let me just say that from this equation over here, we can see that if minus 2 is equal to 3b, the only way that happens is if b is 0. And then we can plug that back into this other equation that we had, and we get a kind of vacuously true equation there. That is, if b is 0, then the top equation is going to be true no matter what we pick for a. So a can be anything as long as b is 0, and that's going to be an eigenvector for the eigenvalue 3. So we could say this eigenvalue v a can be anything, b has to be 0, and then ultimately when we're going to write our solutions out, we just need one such eigenvector, and it doesn't matter which one we pick. So here I just picked a to be 1, and that gave me one eigenvector. You could use 2, 0, 3, 0, minus 5, 0, whatever you want to pick for a is fine. Any questions about how we got that vector 1, 0? Okay, if not, then we would do something similar for the case of 2, except for the case of minus 2, we now plug in minus 2 over here, and we get slightly different equations. We get basically the same equations we had up top, except we just changed the scalar to minus 2 over here. And then we would solve this equation, the system of equations. So from this one, we can see this is going to be true no matter what b is. So we don't really get any information from this equation at all. But if we look at the top equation, we can see that there is a relation between a and b, namely as long as b is minus 1/2 of a, then the top equation is going to be true. So that means we have eigenvectors of the form a could be whatever, and once we pick a value for a, that's going to determine what the value of b has to be. And so again, this is what the eigenvectors would look like in general. We just need one such eigenvector, so we can pick any value that we want for A, and that's going to give us a corresponding value for B. So any questions about that? I saw there's a chat that I might have just missed. Yeah.
How did the coefficients for the right-hand side of the equation become -2?
Because I think I just transcribed the wrong eigenvalue. The eigenvalues here are 3 and -2.
Oh, okay.
So sorry, that should have been a -2 there. Sorry, I'm catching up with another question here. Oh, sorry, someone chatted in a question. I'll get to that in a sec. Yeah, so the short story is, right, the left side of the equation is the same because that comes from the matrix, and then what's happening on the right side is we're plopping the eigenvalue in front of A and B. We get a system of two equations, we solve for A and B, that tells us the relationship between the coordinates, and then we just pick our favorite one. Okay. And so if we're trying to use this now to come up with a vector form of the general solution, then the idea is, okay, we take eigenvalue 1, we find eigenvector for it. We take eigenvalue 2, we find an eigenvector for it, like we did above. And then once we have that information, we've got a vector form for the solution. So I'm going to have like my C1 e to the lambda 1t, my C2 e to the lambda 2t, and I'm going to just put this vector v1 and v2 with its appropriate eigenvalue. So in this case, we had two eigenvalues, real eigenvalues 3 and -2. And here we had the eigenvector for 3 was 1, 0. We had an eigenvector for -2, which was 1 minus 1 half. And let me just say, this is equivalent to if we wrote these out separately.
Can you scroll back up a little bit?
Yeah, just give me 1 second. I can't do that while I'm just writing. Is that enough?
Yeah, you're good. Thank
Okay. And so if we just multiplied out that vector form, then we would get back the same general solutions that we found earlier when we looked at this system, and we solved it without worrying about eigenvectors. Any questions? So let me just say that I'm not going to ask you to find eigenvectors when we have complex roots or repeated roots. Those are a little bit more complicated. So I'm only going to ask you to do this in the case where you have real roots. And so that was the case for that last fourth question on the exam on last homework that is now due the following next week. So the real power behind these eigenvectors is not really finding solutions, since we've been able to solve these without finding eigenvectors, but really the big advantage to having this information is it gives us we can sketch a picture of the dynamics in the phase plane. And so that's where we kind of started thinking about this last time when we had this kind of picture over here. So I just want to kind of attach how we can then use this solution over here, these eigenvalues and vectors, to come up with a nice comprehensive sketch in the phase plane. So the idea here is, okay, now let's use all this information about the eigenvectors and eigenvalues to sketch things in the phase plane. So for example, we had lambda 1 was 3, and we had that v1, a possible vector for that was 1, 0. Lambda 2 was -2, and one possible eigenvector for that was 1 minus 1/2. And when we're dealing with these systems, okay, all of these linear systems are all going to have only one equilibrium at the origin, right? And you can see that 0, 0 is clearly an equilibrium solution if we plug it in, and there are no other solutions. So we're only going to have one equilibrium over here. And what we want to think about is that equilibrium stable or unstable? Okay, what is the long-term behavior going to be? If solutions start near 0, 0, are they going to stay near 0, 0? So we can take this eigenvalue and eigenvector over here, right? That vector v1 is just pointing straight in the horizontal direction. So now I know that any solution that starts on this line is going to stay on that line. So that's what's special about these eigenvectors. And I've got this other one that I can graph by saying I'm going to go 1 over minus 1/2 down. And this over here is vector 2, right? It is 1 unit in the right minus 1/2 unit down. And then I can draw a straight line through that vector. So here we're kind of have v2, and over here we've sketched the line through vector v1. So what we're doing is we're sketching the line through each of these vectors. So that'd be kind of the first step once we got those vectors. Does it make sense how I graph those? Okay, then we need to indicate the direction of the flow along those vectors. And so the way that we do that is we look at the sign of the eigenvalue. If the eigenvalue is positive, that means the exponential power is positive, and so as t goes to infinity, that is going to increase. And so when we have positive eigenvalues, we move away from the origin. And that's the case with the green line over here, since it corresponds to a positive eigenvalue. And if lambda is less than 0, then we are going to move in to the origin. And so that would be the case with this one right here, since that one is negative, these are going to move in. And then we look at the picture and we can see some directions go in, some directions go out. And that's why this one would be what we call a saddle point. Okay, which we would consider semi-stable. And then once we kind of have these important directions marked, this really determines how the dynamics are going to behave everywhere else in the plane. For example, I have to follow these flows and we can't cross over them. So we can see, you know, if I start someplace close to one of these eigenvectors, we're going to kind of just follow the directions that the arrows are telling us to go. So it's kind of a similar type of null-Klein analysis to help us map out the phase plane. Any questions? So the direction of the vectors, there was a question that just came in. How did I determine? So on the red and the green lines, that was determined by the sign of the eigenvalue. So for example, on this green direction for eigenvector
Blue and the green
1,
lines, Professor?
what's that?
You said red and green. Do you mean blue and green lines?
Yes. Yeah, and so on the green line, we've got this vector, and since the eigenvalue here is positive, that's why these go out. And on the blue one, since the eigenvector is negative, that one's going to head in. And then for the red vectors, we determine these directions just by following the directions on the eigenvectors that we determined. So they should move in similar directions as these things. So if I had a direction like this, that would be a contradiction, or it would kind of contradict what's happening over here. Okay, so here's one pretty similar to that homework question that you guys have to do now for next week. So I'd like you to practice these amongst yourselves to give you a chance to run into some trouble if you do. But the idea here is let's do exactly what we did on the previous problem. So that means the idea here would be we want to first find the eigenvalues. Then we want to find an eigenvector for each eigenvalue. And then once you have those two bits of information, you can give a vector form of the general solution. And then we can make a phase plane sketch. Any questions on the task here before I set up breakout rooms? Okay, rooms are open. Yeah, and so I'll leave you guys to work on them and just kind of pop in periodically. But if you have a question, just let me know. So great, good work chatting with all of the groups. I do think I was able to check in with everybody. And so just summarizing what I gathered from the groups is finding the eigenvalues. That stage seemed good at this point. So yes, the eigenvalues were 7 and -1. And then the eigenvectors, there are different ways that we can do this. So if we think about 7 as one eigenvalue, people were telling me they found eigenvectors such as this. Let me just say that these are not unique. You could choose this or other possibilities. We just need to pick one of them, and whichever one you pick isn't going to affect your answer either in part 3 or in part 4 of this problem. The other one was an eigenvalue of -1, and this had an eigenvector, for example, of 1 -2/3. Okay, you're perfectly welcome to pick other combinations like -3/2, 1, or any other sort of incarnation of this. As long as the ratio satisfies the given thing that you find from the eigenvector equations, that's fine. And so from this information, then our solution in vector form would look like C1 times e to the 7t 1, 2 plus C2 e to the -t. For example, that would be one way to write it out, or plug in your favorite eigenvectors that you found. So any questions with that part of the process? Okay, so then the fourth part is to then use this information to sketch the phase plane, approximate phase plane. And ultimately, what we're really interested in is seeing what happens near the origin. So let's first think about, well, how could we graph this information over here? So I want to graph this condition, take this eigenvector 1, 2. So that means I'm going to go 1 over 2 up. And here's this vector v1, and I can just draw the full line that has that direction, since we could have picked any vector that started on this line. So I just draw the line through that vector, and then since this eigenvalue is positive, that means these arrows are going to go away, since that again is positive. And then for the other eigenvalue, which was -1, we can now say I'm going to go, okay, I go 1 over -2/3 down. So that would be this vector over here. And we just draw the line through that vector. Looks like that approximately. And because this eigenvalue was negative, these went in. So any of these other solutions that we can think about, they're all going to have to follow these general directions, so we have consistent flows in the phase plane. Any questions? Okay, so we've got a couple of problems to practice as far as that goes on the homework. Okay, so now let's kind of see what can happen in other situations. So we've thought about the situation when we have one real eigenvalue which is positive and one real eigenvalue which is negative. But as you know, there are other things that could happen. We could have two real eigenvalues, two positive ones, two negative ones, repeated roots, and we could have complex roots. And so on the last sheet, we've got 6 different phase plane possibilities drawn out here. And each of these possibilities corresponds to one of these cases over here. And just without even instructing us how this is going to match up, let's kind of think about what might happen here. So if we have 2 real roots like this, 4n minus 1, and we come back to this problem that we had over here, what do you think changes if we have, say, 2 real positive eigenvalues, if they're both positive?
Nothing's going to be pointed towards the origin.
Yeah, then we're going to get things going out, right? So we should expect to get 2 eigenvectors, and on both of those eigenvectors, we're going to have things flowing out. And so if we look at these possibilities over here, right, the only one that has that property is this one over here, right, in B. And so just for me not being able to do this, right, these vectors do extend out in both directions. So now we would just find 2 eigenvectors. So this would be V1, and this might be V2, and we're going to flow out on both of those. So in this case, just keep in mind, we're not going to get solutions that look like this. All of our solutions are going to be things that are, whoops. Like, this is going to look different. We don't need to get too specific on the shapes of these things, but at least you should now have all of the arrows are pointing straight out from the origin. And there's two special directions that point straight out from the origin. The others are going to curve out. But we're not going to get things that look like this. And when this happens, we are going to call this source. And this is a very stable, unstable situation, excuse me. Any questions? For C, what do you think should be true about the eigenvalues for that corresponding system?
Both negative.
Yeah, so this would be a case where they are both negative. So for example, we said this one matched B, and the 2 negative ones are going to match C, right? And again, the way that we can see this is because these are heading in towards the origin in both of those directions. So here, everything is going in, and in this case, we would call this sink. And this is a very stable equilibrium. So it's like these terms, sink and source, are coming from physics terminology here. And in this case, all of these solutions are now everything should be going straight into the origin. and so then we've got these other ones. So kind of one thing to note is, and this is, you can kind of make some general observations here, is that when we have two distinct real eigenvalues, that means we should find two corresponding eigenvectors. And then, you know, depending on the signs, we're going to get either a sink, a source, or a saddle. So if they're both positive, then we get a source and it's unstable, and that's like the case in B. If they're both negative, then we get a sink, and that's very stable. And that's like in C. And if they're opposite signs, that's when we get a saddle, and that is semi-stable. And that is like the ones that we did on the previous problems. So that's one way to kind of summarize this discussion for when we have distinct real eigenvalues. And so we've got these other ones that look quite different. And so what are your thoughts about what might be happening in these other pictures?
So for F, I'm only seeing one eigenvector. So that might be like a repeated root potentially.
That's right. So that's good suspicion there. And so what's keying us off about this one is that there's only one eigenvector. There's only one direction, which is going straight in. So that would correspond, F would correspond to that. Okay, and notice that eigenvalue is positive, and that's why everything is going out from this one. So we would still call this a source over here, just like in case B, and this is unstable. So what we can see is the sign of the eigenvalues is telling us about the stability. That makes sense because the sign of the eigenvalue is what goes in the power of the exponent. Okay, and then we've got these spirals and circles that are left. So far we've matched up the real ones. How do you think these go? So we've got two spirals in D and E, and we have these elliptical things in A. Anybody have a gut reaction as far as how to match those up with the three cases up top? Ellipses are the no real part. That is correct. Okay, so that's a good gut instinct there. So that is exactly right. So over here, when we have purely complex roots, and by roots I mean eigenvalues, so if we have 0 plus or minus bi, then we're going to get what's called a center point. So we're going to get these orbits that go around the center point, and this we consider stable. Okay, the textbook might call this asymptotically stable. I'm just going to call it stable. Good. So that lines up with A over here. And this is, again, what's called a center point. And the kind of last case is when we have complex eigenvalues let's say where the real part is not 0 okay, in these cases we get spirals like the two we haven't matched up. So we get things like this. And how do you think we determine whether those spirals, say, are going in, like in this case over here, these are going in as opposed to going out in E? I'm looking at these two cases.
D. So D would probably be both negative since they're. No, I'm sorry, the other way around. Those are right, both negative since they're pointing into the origin.
Yeah, so D is going in. So which of these cases do you think makes more sense for it to match up with?
That bottom one.
Yeah, because of this negative, right? And so when we have complex roots, it's going to be the sign of the real part that's going to tell me whether it goes in or out. So when we have complex roots with a non-zero real part, we get spirals. And in this case, when it's negative in front, we get spirals that go into the origin. So we call that a spiral sink, and that's stable. So in this case, that was D. And that leaves E to be the last one. I think that's all of them. So just to kind of summarize this last case, when we have complex eigenvalues with a non-zero real part, we're going to get spirals. And if this real part is less than 0, then we get a spiral sink, and that is stable. And if the real part is positive, then we get a spiral source. That is unstable. And so kind of the big takeaway here is it's going to be the sign of the real part of the eigenvalue, which is really going to determine whether this is stable, unstable, whether it's a sink or a source. And then whether it's real or complex is going to tell us whether we get things going right in or whether we get things spiraling in, or maybe just orbiting around. Okay, so that's a wrap for this worksheet 18. And so we actually haven't gotten to 19 yet. So 19 is going to deal with this linearization process. And so let me just say, if you've done the linearization on the reading quiz, then for the next class, we're really just going to be using that linearization as a means to not do anything new. Just kind of say we can linearize it, and now let's just revisit exactly everything that we just talked about now. So that's what we'll focus on for the next class. So the questions on the homework with nonlinear systems, you're welcome to get started on that, but probably won't be able to get too far on that until we go through it on Wednesday. Okay, well, have a nice afternoon, everybody. If you have any questions, just feel free to stick around.
Thanks. Have a good day.
See you later.